Okay, we have to do that. Okay. Yeah, so Adrien will talk about his new method for separating extended sources in X-ray astronomy. Okay, go ahead, Adrien.
Okay.
Welcome.
So yes, I will present my work for the past few years during my PhD thesis in the CEA in France. That was about the introduction and application of a new blind source separation method for extended sources in X-ray astronomy. And to begin with, I will shortly introduce supernova remnants in X-ray. Then I will present the methodology of the algorithm and explain some of the mathematical principles behind, and then present some examples of application of the method and the conclusions and perspectives I have. So something that Shakespeare made a reference in Hamlet to the luminous spot that was observed by Tycho Brahe in 1572 and that faded out after weeks. So Tycho Brahe interpreted it at the time as a new star or stellar nova, and it played a major role in making astronomers think that the sky was not a non-moving divine entity after all. So it had a strong impact on modern science history, and even if it was not the first observation of it, it is still really important for us. And it took some time to understand that they were actually not the explosion of dying stars. They were actually the explosion of dying stars and not new stars. And it took even more time to understand the mechanism of it, and it is not completely done yet. So we have two main types of supernovae that are the true thermonuclear ones and the core collapse ones. So the thermonuclear supernovae are white dwarfs that accrete too much matter, that accrete too much matter, and reach a certain mass that is a limit until, and then there is the ignition of an explosion, and there is a thermonuclear explosion. And the reasons why it accretes so much mass is either the single degenerate scenario, that is a neighboring bigger star which gives mass through stellar winds, or the merging with another white dwarf. And in both cases, it reaches a certain mass and it explodes. The second type is the core collapse type, and we will focus on this one, because it is the main one I studied. So at some point, the nuclear fusion that occurs in the core of the star does not counter the gravity anymore. So the core collapses on itself, either in a neutron star or a black hole, and the shock is revived by a neutrino heating, which is boosted by instabilities. And thanks to that, the outer layers of the star are ejected, and the asymmetries in the matter induce the neutron star kick that is seen afterwards. And it is important to note that asymmetries in the explosion were proved necessary in the simulations. And there is a major issue, which is to being able to trace back clues about the explosion in the remnants that we can see nowadays in order to constrain the mechanism of the explosion itself. And for example, this is the case with asymmetries. And some recent simulations have shown that even after centuries, we can still see traces of asymmetries in the remnants. So in this example, we can see on the left a perfectly symmetrical supernova that evolves into a remnant that is mostly symmetrical, and in comparison on the right, an asymmetrical supernova that evolves into an even more asymmetrical supernova remnant. So it is showing that we may use the asymmetries that we can observe in supernova remnants as a clue to understanding the asymmetries in the explosions themselves.
Hey, Adrien, quick question.
Yeah.
When you say that asymmetries were proven to be necessary, what does that mean?
Not exactly proven to be necessary, but more that in the simulations, asymmetries were needed to have the explosion occur for real. So with the current methods of simulation, it was necessary to have some asymmetries somewhere in the matter and the ignition to make it occur. If this is completely spherical, it just does not explode.
I see. Got it. Okay. Thanks.
So there is here is a schematic view of a supernova remnant. In the center, we can see the compact object. So mainly it's a neutron star, but in some cases it can be a black hole. Around in orange, it's the ejecta, that is the matter from the dead star. And the forward shock in black is heating up the interstellar medium, like going forward in the interstellar medium, heating it up to millions of degrees, making it hot enough to emit in X-rays and be seen as that, like that, for example. There's also a reverse shock that is going toward the center of the remnant and heating up the ejecta, making it also hotter so that we can see it in X-rays. At the level of the forward shock, particles can be accelerated, and these particles will self-generate a magnetic field that can trap them. And once they are trapped at the level of the shock, they are accelerated at each cross, gaining energies. And when they are finally released, they have much more energies. And it is one of the reasons why, at least one of the reasons why we observe cosmic rays. The two main spectro-imaging instruments in X-rays are in the satellites XMM, Newton, and Chandra. And they can detect each photons individually. And for each of them, we can retrieve, we retrieve 4 dimensions that are X and Y, so the spatial dimensions, the energy, and the time of detection. But usually we don't really need the time of detection, so that leaves us with 3 dimensions that are X and Y, the spatial dimensions, and the energy. So here is, for example, the Cassiopeia A supernova remnant data cube as seen by Chandra. So we can see that by rotating it, we have the 3 dimensions. And we rarely see this kind of data like that. We usually either collapse it to have an image or a spectrum. But even just by looking at it like a cube, we can see interesting informations along the energy line. If we look at the cube along the energy line, we, for example, can observe that there are some asymmetries in the spatial distribution. For example, we can see at the silicon line that there is a bigger clump in the north than there is in the south. And if we look at the iron line, we can see also asymmetries in the velocity distribution, with one clump being slightly redshifted, while the other is slightly blue shifted. So just by looking along the energy axis of this cube, we have important information, and it really highlights the fact that the 3 dimensions are highly correlated. And usually we look at this kind of data like this. That means that we either collapse it along the spatial dimensions to obtain a spectrum, or along the energy dimension to obtain an image. So this is a reworked image, but it's beautiful. And actually it's both spectra and images were obtained thanks to the same Chandra data. And so the whole idea and the whole question of the method I want to introduce is being able to disentangle the different types of emissions inside of this kind of extended sources. So here for a supernova remnant, for example, we have thermal emissions and that are continuum or line emissions and synchrotron continuum emissions. And we would like to be able, for example, to see only the ejecta emissions or only the synchrotron emission without any pollution from the other ones. So I'll briefly present the methodology. The traditional analysis method mainly consider the spectra or images separately, and they don't consider the correlations at all. To obtain some separate images, one very simple option would be to just integrate the cube around the peaks, and we obtain the small images here, which are meaningful. We have some ideas of the structures of the different ejecta components, but it is also highly contaminated by the synchrotron emission, so it's not perfect, and it's difficult to have clear conclusions about that. Other traditional...
Sorry.
Wait,
can I interrupt? So when you say synchrotron emission, it will be the continuum image, right?
Yes. To be more precise with the image, the synchrotron emission is the big continuum emission that we can see in the spectrum, and on the image it's the kind of a blue sphere that is around the whole thing. This blue in this image is more or less the synchrotron, and all the rest is more or less the different components. The problem with this blue part is that as it is everywhere in energy, it's really difficult to disentangle from the rest. And it's particularly difficult in the lower energies where it's really high. So we see almost only that when we integrate. So traditional analysis methods neglect the fact that there are correlations and mainly define cells area of interest in the image and then only work in one dimension by using softwares such as XSpec or things like that. And there are lots of problems with that, and the first one being that the cells are not optimized for every component, the correlations are not considered, and each cell are treated independently. So we miss a lot of information, and also the fact that there are lots of cells make it very time consuming. But it's not the most important, it's mostly the problem that is that the most important problem is the fact that we miss a lot of information. The idea of the method I use is to make an analogy of our problem with the CMB. So the problem with the CMB was to being able to extract an image of a very faint component out of the complete Planck survey of the sky. And there was an algorithm that was developed for doing this that is named GMCA, and it was introduced by Jérôme Bobin in 2016. And it was used to extract this CMB. So we would like to see if it should be also used for supernova remnants and that kind of extended sources in X-rays. The problem is that it's not exactly the same problem as with Planck, as there are much more energy channels in X-rays than in Planck, in radio. And also we have Poissonian noise, which is not the case in Planck. So the problem is slightly different, and that's one of the reasons why I had to do a lot of tests before using it on real data. The idea of this algorithm is to consider the data cube as a sum of components plus some Gaussian additional noise, Gaussian additive noise. So mathematically, it can be written as such, X being the data cube, and AS being spectra multiplied by images. So the idea is to see the different components as an image multiplied by a spectrum, plus some Gaussian additive noise. And the GMCA is able to disentangle that kind of components without any prior instrumental or physical knowledge. So we have this assumption that we have a linear decomposition, so images multiplied by spectra, and we postulate that there are n components. N is the number of components, and it is user defined. But apart from this number, everything is without any physical knowledge needed. And if we have if we don't have any information about A and S, the problem is ill-posed, so we need a constraint to solve it. And this constraint needs the concept of sparsity. So I will introduce it. A good analogy to understand it would be with Fourier transform. If you want to disentangle 3 periodic signals, you won't do it in the real space because there are an infinity of non-zero coefficients, and it will be really messy. But if you go in the Fourier space, you have only 3 non-zero coefficients, so it will be really easy to disentangle these 3 periodic signals. And then once it's disentangled, it's easy to go back to the real space. The idea is to do the same with images, but instead of the Fourier transform, we use wavelet transforms. And these wavelets, the wavelets can give sparse representations of images. And in particular, we use starlets that are well adapted for astrophysical images. And the idea of starlets is that we obtain out of one image different images that only show the details of a certain scale each. So the first images will will present only the small scale details, and the last images will only show the large scale images. And thanks to that, it will be easier to disentangle the different components. So here is a very simple example. It's a data cube made of 2 components. There is one that is an image of a grid of small Gaussian blobs associated with a flat spectrum, and a bigger Gaussian associated with a Gaussian spectrum. And we will see in this little animation. Then if we look at so it's the different slices of the cube. If we look at the images on the left, it's completely impossible to disentangle the very faint big Gaussian in the middle from the grid. But if we look at the wavelet coefficients on the right, we can see a huge difference between the large Gaussian and the small Gaussian. So the idea for the algorithm is instead of using the images that are really unclear for the specific mean, to look at the wavelet coefficients.
Adrien, quick question. What does a starlight look like?
I have some...
That's a starlight, you see, right there.
It looks like this. So a starlight, the idea is that it's undecimated. So every transform in wavelets have the same size. And also it's a mean to represent isotropic structures. So it's the same in more or less in every direction. And it is well adapted, well suited for small sources like stars. To disentangle, it's really easy because it's isotropic. For bigger extended sources like my problems, it's not as well suited, but the good thing is that we have a lot of different kind of morphologies, and the starlets being isotropic, they don't bring any information. Like there are some kind of wavelets, like curvelets, that will favor only certain directions, which will constrain the kind of morphologies that we can disentangle. But with the starlets, as it is isotropic, we won't have this kind of issues.
Are these orthogonal?
Sorry?
Are the starlights orthogonal? The different scales?
I don't think so. I don't think so. I'm not sure of that actually, but I don't think so. Okay,
it looks a bit like a Gaussian, right? I mean, it's with a central peak. And
it definitely looks like a Gaussian.
Okay.
The idea is to be really isotropic and to produce images of the same size in order to have redundant signals at some point. So.
Okay, thank you.
And so after my small example, the GMCA is able to disentangle using the wavelet coefficients, the 2 main sources that were the grid of Gaussian and the large Gaussian. And usually we put n slightly superior to the real number of components that we want to retrieve in order to put the Gaussian noise away. So we had this problem, and now we can use the morphology, a morphological diversity term that is the sparsity constraint. And as we can see, it's the sum of lambda s. It's only applied on the images. So the constraint, the sparsity constraint is also only a constraint on the morphological diversity of the images, not on the spectra. And the algorithm is iterative, and each iteration is containing 2 steps. So the first one being the estimation of S for fixed A using the terms with both the similarity and the morphological diversity term. And the second step is estimating A for fixed S by only minimizing X minus AS. And we iterate until we have something interesting. So it's very interesting to note the 3 hypotheses that are needed for a correct use of GMCA. The first one being the linear decomposition. The second one being the fact that we need the different components to have different morphology in order to the wavelet to be consistent and interesting. And the third hypothesis being that the noise is Gaussian additive. So we ask ourselves if it's appropriate for X-ray studies. And the answers are, for the first one, it depends. Like, it is not stupid to imagine that we will associate mean spectra to retrieve the images. We just have to look if the results are consistent and physically relevant. The second hypothesis is good for extended sources, because in supernova remnants, for example, we have a lot of different kind of structures, like filaments, clumps, knots, so a lot of different morphologies, so it's not a problem. And unfortunately, the third hypothesis is not good, because we have Poisson noise and not Gaussian noise. But with a few tests, we can see if it's really an issue or not. So my first paper was about tests on toy models and benchmark of this method. And we created fake Cassiopeia A, very simple, with images of a synchrotron emission associated with a theoretical synchrotron spectrum, plus an image of some ejecta component associated with either a line emission or a thermal continuum, plus some instrumental background, and we added some Poisson noise. And the aim was to test the algorithm on this kind of toy models. And we were able, for both types of toy models, so either the thermal continuum or the thermal line emission, to obtain several toy models with the relative, the ratio between the synchrotron and the other component being different each time, to see how faint could be the second component for the algorithm still to be able to retrieve it. So basically it looks like this. There are two components. We mix it in a cube where the second component is really fainter. And then the GMCA is able to disentangle them without any prior physical or instrumental information. So if we want some to compare the image accuracy of what is in the toy model and what was retrieved, we used the SSEM index, and the idea was to benchmark the performances of the algorithm. And we can see that if you look at the different points, the ratio, when the SSEM is 1, it means that it's perfectly retrieved, and when it's 0.7, it means that it's just not retrieved at all. There are images to show that. So it's interesting because we can see that either the algorithm is able to retrieve the fainter components perfectly well, or a bit noisy, or not at all. We never saw any kind of artifacts. We only saw some noise without any signification. In older tests, there was no artifact, so it's a good clue that maybe the algorithm can be trusted in retrieving the components. If we look at the spectral accuracy,
Adrien, sorry, can you go back to that for a moment? So when you have this SSIM of 0.73, this is the reconstruction, but then you should also have a residual, right? So do you see any structure in the residual that gives you a clue as to what might have happened?
What do you mean by residual?
Maybe I'm misunderstanding what this figure shows. What is the top 3 figures? What are they about?
Actually, the SSEM is just a number between 0 and 1 that will quantify the similarity between 2 images. So as there are correlations in the noise, here it's a 0.7 means that the 2 images are very different. So when the SSEM is 1, it means that the retrieved image is completely similar to the image that was inside of the toy model. When it's 0.7, it just means that it's very different.
Right. So when the retrieved image is very different, that means that there should be a residual between the
yeah, and the residual we can see is just the noise, like the third image, for example. Actually, the image that is retrieved is just a noisy structure. There's no artifact or something like a fake structures inside of it.
I see. So I see. So each of these, you get all 3 images.
Yeah. Sorry, maybe it was not clear, but the 3 images were 3 it's the images of the same component, but at different level of ratio. Like the first one was the second component is a bit fainter than the synchrotron, so it's well retrieved. In the second one is very, very fainter, like 10 times fainter than the synchrotron, so it's noisy. And the last one, it's so faint that that the algorithm is not able to retrieve it anymore.
Okay.
So I have another question. How do you quantify that the images are the same or different? You know, when you retrieve the image and reconstruct it.
SSEM index. It's
Sorry?
it's the SSEM index. It's an index that was created in order to have that kind of estimation. It is supposed to quantify the similarities at large scales between two images in order to mimic the kind of analogies that we can see with the naked eye. Like it's not a pixel by pixel comparison, it's with larger windows. And the idea is to mimic what a human would say similar.
Okay, so that's the index which you define somehow, right? Okay.
Which was this one, because the images we have are made to be studied by human afterwards. So we want something to correspond to that.
Could you actually remind me what the mathematical formula you have for the SSIM? Because I know it has been a hard problem to make the thing corresponding to our visual. So
I don't have it right now. I think I used it was in a Python library that I don't remember. That I think it's the classic one. I don't know if there are arguments about that, but it's the first one I found when reading papers about the SSEM.
But can you give us an intuitive explanation why this works well? Because you were saying it's not this pixel by pixel kind of thing, right? It's a broader structure. What is it some kind of a distance discrepancy measures? What is I mean,
I think it's some kind of a distance, but it's mainly it's comparing the two images on windows of a certain size. It's not pixel by pixel. It's windows going through the image, and these windows have a certain size that is supposed, I guess, to be meaningful.
And within each window, they would take some kind of average pixels. What do they do within each window, like for those two?
That's a good question. I knew this at the moment when I wrote my manuscript, but I must admit that I completely forgot. I think it was. I can search it.
But no, you don't have to say. But your experience that it has worked well compared to humans' vision.
It seemed to, and actually, it was not very important the kind of index we used, because the most important thing was the comparison between the moment when it's really well retrieved and the moment when it's not retrieved. So it's more like quantifying what we could see with the naked eye, because writing is in a paper that I can see it and then I can't see it is not really physical or mathematical. So we had to choose an index, and this one in all our tests really reflected what we could see with the naked eye. And the only idea for us was just to prove that the GMCA was either able to retrieve or not to retrieve something, but the exact number the SSEM gives is really not relevant for us.
Got it. Thank you.
So, and we have the same kind of comparison for the spectral accuracy. But here we just compared, so in the dashed lines, these are the theoretical models inside of the toy models, and the plain lines are what we were able to retrieve. So on the left, it was with the line emission toy models, and on the right with the thermal emissions toy model. And we can see that it is mainly well retrieved, but there are deviations in high energy from the model particularly on the right one. And this was linked to the fact that at high energies, the thermal emissions was so faint that it was really overlapped by the synchrotron, and it completely disappeared. And it was also, after some tests that I will not show here, linked to the Gaussian noise, because the assumption that the Gauss is notion was not a problem when we were only looking at lower energies, but with the higher energies, the fact that it was Poissonian and not Gaussian became an issue. So here is a test on
another question, Adrien. So when you extract the spectral component, do you include the? I mean, is it a model? Do you fit a model, or is it just a phenomenological histogram that comes
there's no model. There's no model. We really obtain. We fix the number n of components we want to retrieve, and we obtain n images associated with n spectra, without anything to do any model on.
Okay, so the spectra are just the average PHA distribution in the data. Okay,
exactly. So here is a test on real data. This is an integration around the calcium line emission. So the image is in square root, and it will be the case for all images because it highlights the pollutions. And here is the same line, but with the image we retrieved with Cassiopeia A. So we can see that all the pollution from the synchrotron is perfectly extracted. And here is another application around the iron line. We could expect only to see the synchrotron emission and the iron emission, but we were able to retrieve actually two iron structures, one that is slightly associated with a spectrum slightly redshifted, and the other one with a spectrum slightly blue shifted. So this is consistent with what we know about Cassiopeia A, and the algorithm is able to retrieve that kind of shifts. So we can answer some parts of our questions. So the
question about the real application. So did you have to tell it to find 4 components when you ran this, or how did you find this red and blue shifts?
You mean the noise?
No. You know, there's a synchrotron component, the red shifted and the blue shifted. And you said that you had to specify what the number of components are beforehand, right?
Okay, because actually it's something I didn't say. It's very, very fast running. Like for the Cassiopeia A data, it's something about 1 minute to run. So we can test a lot of different numbers. So in the beginning, we tested for like 2 or 3, and we tested other numbers. And at 5, for example, most of them are completely not meaningful. But we saw that at 4, we had something really interesting. And for all the applications that I will show, we tested a lot of different numbers, and we just selected the interesting ones.
Okay. Is there a way to tell?
Sorry?
Is there a way to tell what the number of how many what the real number n should be, or estimate the number of components from the data?
Well, I can show you something that is interesting. It's actually the best way is still to try a different kind of numbers. Here you can see for exactly the example I show you, the different numbers and what the images we obtain. And on the right we can see it's the AKK information criterion, and the idea is to see which n is the most accurate. But this method is not perfect because the algorithm is using a sparse regularization criterion that makes the AKK information not perfectly accurate. And also there may be some physically significant components that are not statistically significant. But still, this is an idea for an automatization of the choosing process. But for now, the best solution is still to do it with the naked eye, just do a lot of run. And as each run is like 1 minute long, it's not a problem.
What are you looking for, though? You say by the naked eye, and what is interesting, but what does that mean? How do you know? How do you know when you found the right number?
That's a good question actually, and I think the fact that the algorithm does not seem to produce any spurious or structures or artifacts means that what I would mean by interesting would be like structures. If you have something completely messy and noisy, it's just some remaining noise. Because if you ask the algorithm to find seven components, it will find 7 components. Some of them will maybe look meaningful because there will be structures and all, and the rest will just be noisy because the algorithm can't know if it's physically significant or not.
So
But you can see that if you have only noise, maybe these structures are not interesting.
So is that what is this, the rows of this figure you're showing us corresponded n equal to 2, n equal to 3, n equal to 4 when you fit it?
Yeah, the idea, when you see that the only 3 meaningful structures are the 3 first ones, and afterward it's just like remaining noise that are added. So,
yeah, but what can you say what the figure is?
You mean
the columns?
The AIC figure?
No, the matrix of images.
Yeah. Actually, we can really see the error bars, but the noisy figures are very, very faint. Like it's only 1 or 2 pixels.
You can't tell me where they came from or how to interpret the rows and columns that you have put on this plot.
So the
rows and columns. What does it mean?
Okay, I'm sorry. So the rows are the images retrieved by the algorithm at a certain aim, at a certain number of components to retrieve. So
with more than 4, you only get more noise.
Yeah, that's it. Even with more than 3, we only get noise.
But some of that noise you apparently think is real, because you didn't choose n equal to 3, you chose n equal to 4.
Yes, because we saw with some tests that it was better to, as it was supposed to be Gaussian noise, which is not the case with X-ray data. It was better to select a fourth, another component just to put noise, like the residuals. But later in the presentation, it proved that I will show that it proved not useful.
Sorry,
can I do a couple of questions on the previous slide also? Yeah, so for the CMB data, don't they use the GMCA algorithm when it's applied to Planck? Don't they use information on specific frequency dependence of those components?
Yeah, because the CMB we know perfectly the theoretical shape of the spectrum, so they use it. But the way for now it can be used in GMCA, you have to completely fix the theoretical spectrum.
Okay.
In Supernova remnants, we don't know perfectly how the spectra look like, so it's better for us not to fix it.
And now here, do you rely on sparsity in the spectrum to decompose into different components?
No, we made some tests, and it could be an interesting way to apply the algorithm on other types of data, but for our problems, it was not necessary because we have more sparsity, more different morphologies in images than in the spectra. But we tried it, but it's not used in this version because it was not really relevant.
So here, for example, let me rephrase it. Here you have a continuum spectra plus 2 components with line-like spectra. So they are spectrally, quite separated. Yeah. What if you have a power law plus, a harder power law? Will you be able to?
In our toy models, we made these tests. It was one of the 2 options of the toy models, and it works quite well. It's the case where the spectra were the less reliable at high energies, but at low energies it's okay, and for the images it's perfect.
Okay.
But it's true that even in the spectrum, it's better to have some different morphologies, but not exactly because of the wavelets.
Sorry, can you go back? I have a couple more questions. This is a very nice figure. So that's why I think, very informative. So one is a follow-up from what David was asking. So you chosen n equals 3 as the smallest AIC, right? But then in number 4, there is an extra component which shows that there is just plain noise, or looks like that. Shouldn't that have been the proper decomposition?
You mean the 3?
I mean, I would have thought n equals 4 would have been the preferred decomposition, because it allows for the existence of noise.
Yeah, that's one of the reasons why we think that the AKK information criterion can be useful as a figure of merit, or to compare with what we see with the naked eye, but it's still not consistent enough and interesting enough to be used automatically. Okay. So yeah, for me, it's also better to choose the n equal 4 instead of 3.
Okay. Okay. So now about the 2 components that you have with the ion, the Doppler shifts. How do you know that they're not? It's not a gain effect. I mean, they seem to be spatially segregated, so it could be just the gain changing across the detector, right?
Well, actually, in Cassiopeia A, we know that there is this asymmetry around the ion, so it's something that is quite obvious only by looking at the cube, and also in a lot of different papers that were talking about that. But in another paper that I wrote with collaborators on Cassiopeia A, we did the same work on other line emissions that I will show afterwards, and we made some tests to verify if it could be linked to other problems like ionization effects and that kind of things. And it seemed that ionization effects, for example, were not really relevant. And the best explanation we had was more this real shift in velocities.
Okay, so essentially what you've done is you collected the photons from these components and you've done an actual spectral fit. Okay, and you still find that it's best explained with a with a Doppler shift.
For most of them, for others, that there are some doubts, but mainly it's explained by Doppler shifts, and it's not in contradiction with what we already know about Cassiopeia A. Like, it's not we have far better images than that what we had before, but it's not groundbreaking because we knew that there were some lots of asymmetries in the velocity.
Right. Okay, thank you.
So to come back to the hypothesis, we can see that the 2 first are okay, and the third one, even if it's not Poissonian, it's still working quite well. But during the course of my PhD, the team that developed the GMCA also developed the PGMCA, that is the version that takes into account the Poisson noise. So it's more or less the same kind of algorithm, the same principle with the same iterative model. It's just that we replace the linear mixture model with a Poissonian law. And it's quite similar. It's just much more sensitive to the initial conditions. So it's necessary to use a GMCA as a first guess before using the PGMCA. And it's also, it takes way more time to run. So it's more difficult to do a lot of PGMCA, but it's still like around 10 minutes or something. So it's not huge as much. So now
Alex has his hand up.
Sorry?
There's a question.
Yeah, there is a question. Yeah, sorry.
I should be paying attention. Yes, Alex. Yeah. For people who are in the listening, just feel free to pitch in. It's okay. We have been interrupting constantly.
Okay, Alex. So, Alex, do you want to ask a question? We don't. We don't hear you. I don't know.
Oh, he said his microphone. working. That's too bad.
Okay.
I have a question in the
You can
window chat if you
Yeah,
like.
you can type. Oh, okay. He will come back to it. All right. So we continue.
Okay, so so now the Poissonian is not the Poissonian noise is not a problem anymore. So
Can you guys hear me?
okay.
Oh, sorry, he's back. All right, Alan.
So I just had a question about the video. I just had a question about that triangular plot you had with the n equals 2,
Yeah.
3, 4, 5. Is there a way to I mean, does this algorithm rank those images, like, or those different components? Like, if you have n equals 3, does it
yeah, there's
rank them on like the most significant to least significant?
It's not significant because it has no idea of signification or whatsoever. But it's usually it's like the more statistically significant, so the more powerful component than the fainter one, etc. So mainly for our tests, it was always the synchrotron in the first place, and then the second more important, and then the third. But if you have very similarly important components to retrieve, then it will be just randomly put.
So what is it that makes the brighter component like the n equals 1 component?
That's a good
So I
question.
mean, it's like if you make
the way
you have to go and sort them by hand to make sure, like, you know, all the synchrotron ones are in the first column and all the.
I'm not. No, it's not. We don't specifically want the most powerful component to come in the first place, and it's not really coded as such. It's just an effect of the way it works. Just
Okay.
we retrieve images on spectra, and the order is more or less always the same, but it's not a question we ask the algorithm. It's just like that.
Okay, so that can't be used as a way to decide when to stop adding components.
No. If you have only strong, meaningful components, then the noise will be negligible in comparison, so it will be the last ones. But if you have a very faint component, then this one sometime will appear after having some noisy image. So that's one of the reasons why it's worth trying a lot of different number of components.
Okay.
So very briefly, because I'm not sure I will have time, but there was a huge problem we had also. It's the problem of the significance on the error bars. And the problem is that the Poissonian nature of the data is not kept after the algorithm runs. So the different spectra and images we obtain do not follow Poisson rules. So we had to find some ways to retrieve error bars. And the question was how we could obtain error bars from a single data set. So the logical answer would be to use some bootstrapping method, which is if you have an original data made of different events, you will randomly select with replacement the same number of events out of them, and that will give you different new resamplings. And you can look at the standard deviations, for example, to see the to obtain some error bars on your results. For example, if you do that on a square associated on just the image of a square with some Poisson noise on it, you can see that unfortunately the bootstrap does not really work, because doing a bootstrap gives if you look at the histogram, gives the same kind of histogram as if you added Poisson noise to the already present Poisson noise. So it's something that I did not find in any paper written. So I'm not sure that it was found before or not, but I didn't find it. And I was surprised to see that the bootstrap was completely not adapted to studies on Poissonian datasets, because it just added some more noise. And we can see it's the same with an image of Cassiopeia A. And it was really depressing for us because it seemed to be completely impossible to find any meaningful method to obtain some error bars. And if we look at the PGMCA applied on bootstrap resamplings of Cassiopeia A, we can see that the results on the resampled data sets are not completely not consistent with the results on real data sets. So this is a spectrum, and we can see that the spectra are really different.
So what is the mechanism of the bootstrap? What are you doing exactly?
The bootstrap is a resampling of the events. If you have a set of events, you take randomly inside of this set the same number as you had in the set.
With replacement. So it's just an X, Y, and E.
It's just a shuffling of it. It's a shuffling of it. And the idea, I had the idea that maybe by doing a lot of bootstrap resamplings, we could just apply the PGMCA on every result, then look at the standard deviations, and magically we would have had some error bars. But unfortunately, there is a bias, and it's not a classical bootstrap that could remove it. So I tried to develop a constrained bootstrap without a bias. And the idea was to work directly on the histograms rather than the individual events. So I won't stay too long on it, but the step one was just to generate random histograms that follow the same rule, and then create a new imaging by imposing the new histograms on the original image, so as to make fake bootstraps resembling the kind of distribution that we want. And actually it works quite well, and we can see that there is no more biases in the results. The classical bootstrap gave huge biases when we use the PGMCA on it, and my constrained bootstrap doesn't give any bias. But the problem is that we removed the bias, but we could not control the variance, and the variance proved to be not physically significant. So it cannot be useful as such. It's still interesting to quantify the consistency of the PGMCA around initial conditions given, but it's not able to give good physical error bars. So that's something I would like to continue exploring, but it's not done yet. But yeah, no physical significance.
Right. Before you go on, but why did you expect the bootstrap to work at all in this case, right? Because bootstrap requires the original sample contains internal replication you can extrapolate, right? There's some kind of, because for you just have one. Am I correct? You just have one image there. So without knowing how the internal replications, you would end up with either you don't get it, or you create something artificial, which is you can control still fitting well, but the uncertainty is not the real uncertainty because you don't have the information.
Actually, we don't have exactly one image. My examples were on images because it's easier to apprehend. But the real data we have in X-rays are data cubes made of individual photons. So they are exactly individual events as required by the bootstrap. So I was quite naive and I didn't know well the bootstrap before, but it was the kind of data on which the bootstrap can be used. And actually for means
right, but the key question is, let me try to understand this because that's important. What's the basic units here? Is the sampling units the individual pixel or the entire image, or something in between?
In the case of images, it's if you have a pixel at 2, it's a Poissonian images, so it's only entire number. So if you have a pixel with 2, it's 2 events. If you have a pixel 0, it's 0 events. If you have pixel 10, it's 10 events, etc. And for a cube, it's exactly the same thing. A cube in X-rays is just a cube with individual photons, and we just count the photons. So we take all the photons and we shuffle them with the bootstrap method, and that gives us a new cube. And I thought that maybe it could be interesting, but it turns out that it's interesting for linear estimators, but for nonlinear estimators such as the PGMCA, it gives huge biases. And that's what I was able to remove, but without the significance of the...
No, I don't think we're talking about the same thing. I understand that the pixels have different Poisson counts. They're They are independent of each other. But for bootstrap to work, essentially that every bootstrap sample had to be representative of the problem you want to deal with. If you have image has these structure in it, you can't just randomly shifting these Poisson constants around, because then you completely change the, you will be changing these pictures, right? Because there's neighbors, right? There are these structures, they're connected with each other. Unless you have multiple these images as your sampling units, you won't be able to reflect what the proper error is. If you can do whatever you want to do, but you are destroying the underlying structure, right?
The idea was precisely not to destroy the underlying structure, and it proved that the bootstrap was not able to do so, but my constraint bootstrap is. And the idea of the constraint bootstrap was to do a fake Monte Carlo, as if we had an underlying model, but without knowing it. And I would like
correct. That would be the right way to do it. But then, how much fake Monte Carlo errors you add on will governing the uncertainties you will get, right? Because you can add on more, add on less.
With my constraint bootstrap, there's no need for any model. It's working only with the one data set that you have, and it gives NBS results, but the variants are not significant. So it's not perfect yet, but it may be interesting to explore.
No, I don't think you get my point. Is you can work it with one image, you can add on whatever noise you want to add on, but why that noise you add on reflects the real uncertainty in this picture?
No, precisely. I don't want to add noise, and that's the problem with the classical bootstrap. It adds noise, and the idea was to have some method that was able to reshuffle without adding that noise, just as if it were a Monte Carlo, but it is not, because we don't know the model.
But if you reshuffle where the information comes from, unless you have multiple images, right?
Yeah, it's a bit long to explain the point of my constraint bootstrap, but the idea was to work on the histograms, because it is much simpler than a complete data cube, and constrain the kind of histogram that we want. And once we have this histogram, that is similar to what we would have obtained with the Monte Carlo, we use a random way to redistribute the pixels in the original image to obtain this histogram.
But the question is why that do you have a theory to prove that the permutation you're doing is actually reflects how the uncertainty in that real image?
I really don't have any theory to prove it. It was just some kind of cooking, because I wanted to try something and maybe it would work, and it was promising, so I continued. And in the end, it was not perfect, but it is still promising. But I really don't have any theory to back it.
Because Bootstrap goes beyond the simple settings is always very tricky. It's you can always do something, but that the uncertainty, particularly for these kind of problems, may or may not be the one you really want. You will get something, but it's just not clear to me where the information comes from without assuming certain structures within the picture. Oh, you have replications, because there's simply not much information there.
I'm sorry, can I ask, because you have photons, right? You have photons in this cube. Yeah. And if you sampled one photon, if you sampled photons from that cube with replacement up until the size of the data set, you would, it seems to me, maintain most of the structure, and you would get replicate data sets that vary somewhat.
I think what might be happening, David, is that you'll pick up the events, rather the spatial part better, but over the spectral dimension, it's going to get thoroughly scrambled, I think, because for example, the interesting bits, or for instance, the ion K line is very low. I mean, it's highly the dynamic range in along the spectral dimension is much larger. So you might redistribute those events in a completely destructive way.
There's just not much internal replication here, right? I mean, unless that's the part I don't see how you actually can bootstrap. I mean, when people, even simpler problem, like when people try to bootstrap time series, they have to make certain assumptions saying, like, you can cut these time series, into pieces. And every piece is kind of can be viewed as a mini replicate of the whole thing, assuming certain stationarity, right? But here, the image here is that if you're going after, that structure, I don't see how you chuck this picture unless I'm really missing something.
It's easier than time series though, because the way I think of it is you have each of these photons has a distribution that follows a multinomial distribution because he has all these little bins, right?
Right.
And so you could it's kind of like IID data. It just depends. Each photon lands in a three-dimensional pixel.
Exactly.
No, they're not IID. They're independent distributed, conditioning on the underlying structure, conditioning on the intensity.
Right. So yeah, conditional on the underlying model. Then
Right.
aren't they IID?
Well, it depends on how you think about its IID because they have different lambdas. So, I mean, it's not like a normal, you can subtract the mean and say, well, the error term is IID. Here they're independent, right? But the intensity is different. And that's exactly the problem that, you can't really bootstrap.
Conditional on the total, it's a multinomial distribution. Right.
Condition on which total? The total of all the pixels across all the different cells?
Yeah. I mean, you should be, yeah, that's right.
Oh yeah, that's fine. But then you only get the one image. That's a one gigantic multinomial. You only have one, yes. If you think about it as a multinomial condition on total, then you need the multiple of them. If we're going to create that saying multiple times, I think that's fine. But otherwise, you only have one sample here. Right? The entire picture is one unit, as one gigantic multivariate normal, multinomial. Conditioning on the total.
Right? I think what David is saying is that if you imagine how the data is collected, these photons are coming into the detector one at a time. And each photon that comes in has the identical and independent distribution in energy and time of the previous photon. So it's really just like this replication of one event at a time. Each one has exactly the same distribution in energy and time. And so it seems like you should be able to reconstruct like.
I see. You're thinking about in terms of time units.
I mean, just like let's say you have 100 observed photons.
Yeah.
I would say each one of them is independent and identically distributed from this full complicated 3D energy and spatial distribution. Like if you observed for twice the time, you'd get another set of photons that looked statistically exactly the same.
Okay, if you use a time as a sampling unit, I see that. Now I see your point.
Yeah, but the problem is that the bootstrap is sampling along spectrum, and I think that is messing things up. Yeah,
and spatial. So I think what might be happening is you essentially, when you bootstrap, you remove a photon, you can remove it from little clump over here, and then you will need to add photons to all other different clumps. And so you suppress one structure, you at the same time you need to multiply all other structures, and you no longer have the same faithful representation of the original image.
But yes, that's exactly my worry. But I think Alex has a very good point. If you think of them, if you can record the time, you can just kind of skip some, right? You can randomly delete some time and use that as your image. And if you do that, I do think you have I guess the time period cannot be too large, right? Because then it's not a kind of really.
It's now jackknife, not bootstrap. Essentially, you can remove part of the data.
Time units, that's a good idea. I can see that. Otherwise, that's what was my worry. Yeah. But Alex, you're right. That's a different way of doing it. You need to know you need to know the time of these photons gets collected, and then you bootstrap. Actually, jackknife probably is a better way to do.
I tried with jackknife too, and it was not specifically better. Like it was the same kind of problems we had and the same kind of biases.
Yeah, but it depends on units. Like what are your jackknife? I think Alex is suggesting you should jackknife or bootstrap on the time units, not in the spatial way, or not in the spectral way.
Actually, I didn't use time, but I considered all the photons to be like small bricks, all equivalent one to another, and just taking them randomly and redistributing them.
Oh, I
So
see.
it's like,
So
is it like you have a list of like 1,000 photons, each one has X, Y, and energy, and then you just take 1,000 lines from that list at random replacement, and that's your new data set of 1,000 fake photons.
Exactly, and I thought I did. It was pretty naive in the beginning. I just wanted to know what it would look like, and it seemed interesting. But there was this this weird bias that we could observe here. We could see that the histogram of the resampled data through this method was exactly the histogram of the original image plus some new noise, new Poisson noise. So it was as if the bootstrap reshuffling was just adding some Poissonian noise. And what I wanted to do is to suppress this effect. And that's why I made my constant bootstrap and all. But I think the principle of bootstrapping the photons can be meaningful, but it was meaningful only for linear estimators, and the PGMCA is clearly not linear, so it was not. And the bias that was induced by the addition of this similar to Poisson noise caused huge biases in the PGMCA as well. But I still think that the bootstrap and equivalent with adding some constraint and all could be an interesting way to find error bars in my case and other similar cases, because finding error bars for that kind of nonlinear estimators is really difficult. And for the PGMCA, we still don't have any clue of how to do it. And this is one of the items that we had. Not perfect yet, but I will try to continue.
But I mean, your point about the linear versus nonlinear is an important one. But the bootstrap, if it's applicable, was exactly invented to deal with nonlinearity, because for the linear ones, statistician knows how to do all the approximations, and the bootstrap was exactly invented to deal with this much more complicated estimated without knowing how to calculate, because they are nonlinear.
But it seems that in my case it doesn't work with the Poisson noise. It just adds some more noise. It's not equivalent to the data.
Right. So that's what I'm saying. There's something not quite right in the way the bootstrap, or either bootstrap is not applicable, but I think Alex convinced me that there is a way to do it using time units. And there is, if the Poisson do come in, any of these observations are kind of as a chunk, are there kind of RID, then it should work. And if it doesn't work, then means there's something not quite right in the implementation, because that would be a classical RID structure, that unless there's something changing over the time. So, but I guess we should move on. But there is something quite interesting here.
By the way, Adrien, you have about 15 minutes.
Yeah, okay. I'll be really faster on this part because it's less important for this specific presentation. So we were able to retrieve different red and blue shifted structures, and we did the same around other main line emissions in Cassiopeia A. And we can see that for each one from the silicon to the iron, we were able to retrieve the same kind of red and blue shifted structure. And they are quite consistent one with the other, with the red ones being broader than the blue ones. And also to find some beautiful and clearly detailed images of lighter elements, so oxygen, magnesium, and another ionization state of the iron. Thanks to this image, it was possible to look at the centroids of the different structures, and also to compare, thanks to the power ratio method, the distribution asymmetries. So the idea was to study the asymmetries in the different line elements, and also to do so with the different red and blue structures. And we can see by looking at the relative fractions of red and blue shifted materials, and at the fact that the blue shifted structures are all more asymmetrical than the red shifted ones, that more mass is in the red, and that the red ejected material is mostly some kind of broad plume while the blue shifted material is more like a different dense nodes which is consistent with past studies, but we have much more accurate and at least much more detailed and much more unpolluted images than the previous studies. Also with this, we were able to trace the directions of each red and blue components from the center of explosions, thanks to the different entries that we got, and compare it with the neutron star directions in comparison with the center of explosion. And we can see that the redshifted material is mainly going away from the neutron star, which is consistent with the idea of a kick induced by the recoil of the stellar material. And thanks to the spectra that were retrieved by PGMCA, we were also able to use the XSpec software to obtain some velocities attached to each red or blue shifted line emissions structures. And we can see that it maybe not because it's quite fast, but in the paper I wrote about this, we can see that it is really consistent with past studies and from studies about the titanium 44, which is a good indicator in the Cassiopeia A, and that we find that the blue shifted structures move more rapidly than the red shifted ones, which is also an interesting result. And a beginning of a new application, but not quite advanced yet, is about the synchrotron filaments in Cassiopeia A as well. The synchrotron emission in supernova remnants is often seen with a lot of tiny filaments all around. And there are some models to account for the existence of these filaments. But those models do not agree on a crucial point, that is the fact that these filaments should maybe narrow with the energy. And we wanted to probe this in Cassiopeia A thanks to our method. And we were able to obtain very detailed images of the synchrotron around 3 energy bands. So it's the more detailed images of this, the synchrotron at these bands, in particular at lower energies. So it was a good way to compare the narrowing of the filaments. And we could see by looking at tiny boxes around some filaments that there was, in fact, a narrowing effect. And it should be worked on in a future upcoming paper, but right now we don't have much other results around it, about it, but it's really interesting because it is the first time that this narrowing is detected for sure in Cassiopeia A. And we also did the same with the reverse shock that is more closer to the center, and we can see that there is the same kind of narrowing effect. And we could not find in past studies that kind of studies about the reverse shock. So it's really promising, but for now there's no paper, so we're working on it. And here's my conclusion on the perspectives. So the PGMCA and the GMCA work quite well, but the performances are very case specific. That means that they highly depend on the morphologies of the components to disentangle. And there is a minimum count of roughly 1 million that is necessary. And in Cassiopeia A, if we were able to obtain such impressive results, it's mainly due to the fact that it's very bright and we have a lot of statistics, so it helps. On other supernova remnants or on other extended sources, we could have really interesting results, but maybe not as much as in Cassiopeia A because it's the brightest. There is currently no way to retrieve physically significant error bars, and that's the problem we discussed. Maybe the bootstrap or another type of bootstrap could be interesting, but more tests are needed. As for the Cassiopeia A ejecta, there are lots of interesting results that are presented in my second paper that I will not detail, but they exist. And as for the perspectives, there's the first possibility, which could be really interesting, would be to do the same kind of studies on other type of supernova remnants. And for example, compare type 1a supernova with core collapse. Cassiopeia A is a core collapse supernova, but maybe that kind of results about the asymmetries could be also interesting to see in type 1a supernova, and maybe after some studies like that, we could try to see a trend to compare the way asymmetries evolve between the thermonuclear supernovae and the core collapse supernovae. And currently there are 10 supernova remnants with sufficient statistics to apply the GMCA or PGMCA, so we could do this. Another perspective is trying to study other extended sources, and there was a work that I was supposed to do during an internship at the CFA at the end of my thesis, but because of the COVID, it didn't happen. And I was supposed to work with Ralph Kraft on the application of the PGMCA of Perseus, on Perseus. And we can see just by applying the algorithm that we obtain some interesting images. The first one being what we can see in X-ray. And thanks to the PGMCA, this first one was also decorrelated with 2 other images that were never previously seen in X-ray directly. And the second image is really similar to a structure that we can see in optical data, but that was not directly observed in X-rays before. And the last one, I think, but I'm not sure because I'm really not a specialist of Perseus, that was not detected at all. And it's consistent with simulations about sloshing cold front. But I don't have any physical conclusion about that. It's just that a simple application of the algorithm on this data is really promising. It could be also useful to introduce some kind of method, for example, based on machine learning, to constrain the spectral shapes of the components to retrieve. For example, if we know that we want a Gaussian, like for a line emission or a power law, it would be really interesting to ensure that the algorithm is searching for the right thing. Because right now there's no information at all, which is interesting because we can be surprised by what we obtain. But also if we had some information, even incomplete, it could be interesting to impose it. And there are already some tests that have been made, and it's very promising. And we think that in some cases, it could help to retrieve more accurately very fainter components. And also, it was not an issue for us because we only used the GMCA on short energy bands. So we did not have the problem of the high dynamics between lower and higher energies. But if we want to apply that kind of algorithm on a huge energy range, there is a huge difference in the statistics in X-rays between the lower and the higher energies. So using some kind of adaptative binning should be interesting. And lastly, we could try to use the algorithm on other data than Chandra's, for example, on XMM by taking into account mosaic observations, which is not very difficult. It's not implemented yet, but it's not difficult. Or also taking into account the PSF, because it's not an issue in X-rays, but it becomes one in gamma rays. So if we were able to take into account the changing of the PSF with the energy, we could also apply it on CTA or Fermi-Lat data. And also, I applied only the algorithm on X, Y, E cubes, but we can imagine using it on other types of data. And for example, on transient sources, X, Y, T, it may be something that could give consistent results. And lastly, future instruments like Lynx or Athenas will give amazingly detailed images or spectra, and it would be a shame not to exploit completely the information contained in all the dimensions. So using that kind of algorithm would really be useful to exploit fully their potential. And that's it. Thanks a lot.
Thank you.
Hey, thank you very much. Very nice.
It's hard to do this by Zoom.
Yes.
Do we have any more questions?
I have one question. So in this PGMCA, whatever it's PGMCA,
yeah,
have you tried to apply this variance stabilizing technique Anscombe transform to your data cube to move from Poisson to Gaussian case?
How we move from a Gaussian to Poissonian?
Or the
Take
other
the
way
square
around,
root.
Poisson to Gaussian.
Take the square root.
It's the Anscombe transform.
Sorry.
But why do you want to do that? Because he basically can do the exact Poisson. Why do you want to do the approximation?
Actually, yes. In the first occurrence of the algorithm before Poisson, it could be interesting to do something like that. But once the Poisson noise was well taken into account, there was no need anymore for it. Now it's it's not a problem. So the algorithm is slightly more complicated to use, but it takes well into account the Poisson effect.
Any more questions? It was interesting talk, especially this new application. So you said that you need a million counts, but does depend on the total number of counts or the size of the image? Because you can have 60,000 counts within very small, 16 by 16 pixels, let's say, and you're looking for the small scale structures. So is there any limitation on the scales or just the total number of counts?
Actually, the million count is just a rough estimation. There's no, the algorithm will work whatsoever, even if you have 3 counts, just that the information will not be interesting. But we think, me and the people who developed it and who worked on it with it on extended sources, that a million count may be the, with the kind of images we have with Chandra, some kind of limit for obtaining something interesting. But for the kind of images we have with Chandra, and the rebinning sometimes is necessary. If we want components that are sufficiently different morphologically, it's important that we have a clear view of the morphologies. So we need quite big images, not 16 pixels. And also to have statistics high enough, we may need some rebinning either spatially or spectrally.
Right. So yeah, you're working with supernovae, which are big, right? These are big structures. But if I'm looking at the quasar with the jets or the little cluster around, right, and I'm trying to understand the scales related to the emission from the jet and from the quasar, can I apply, because this is different type of morphology, right? You have the linear,
I have never tried it, and to my knowledge, nobody has in the group I was working with.
Yeah.
So I don't know what will be the result, but if it's a data cube, you can apply it, and maybe it will be interesting. And actually, before me and my PhD supervisor applied it on extended sources in X-rays and mainly supernovas, nobody had before. So we had to try, and it proved.
Right.
So maybe it will be also with quasars, but I don't know.
Yeah, you need to. Well, it depends on the source, because some sources have not enough counts and you basically have a different problem. But there are sources where you have a lot of counts very close to the quasar core, where you want to disentangle the structures.
And at that time, you have to start worrying about the PSF effects and everything,
yes,
right? So
exactly. That was my second question related to it, because Adrien said that you don't worry about PSF in X-rays, but you do. It depends on the scale, right? And for this quasar and the jet structures are too close sources, you worry about the PSF. So how would you incorporate the PSF? Have you thought about it and where it would come?
I did not personally, but the people who developed the method and the different updates thought about it and did not do it, but they know how to. So I can ask them, and it's not difficult. It's just time consuming. But if one really wants to do it, it's really not difficult. And in Spray, we didn't need it, and with Planck data, they didn't need it. But if we wanted to apply it on gamma rays or something where the PSF is relevant, it can be done. And as for the quasars and for other types of data, the main question, I think, is what kind of structure, what kind of difference you have in your components. If it's spatially different, like morphologically different, like in the extended sources, then using wavelets in 2 dimensions in the image is a good idea. But if you are working like on points, maybe it will be more interesting to apply the wavelets or some similar kind of transforms on the spectra. And if you are working on transient sources, maybe it will be interesting to apply it on the modification with time, on the time dimension. So there's a lot of things that are possible. It's just that the algorithm works with 2 kinds of dimensions, and it's an iteration from one to the other, with one being in wavelets or something equivalent. But we can imagine doing it with different kind of dimensions, also putting wavelets on both sides, and there are lots of possibilities.
Mm-hmm. Yeah. Any more questions?
If not, I should probably stop recording.
Yeah, you can stop recording, and I think we probably finished the official part of the talk.